All right, thanks for coming to this week's Learning Analytics seminar series. Today we have Stefan Slater. He's a researcher at the University of Pennsylvania, and his current research focuses on the semantic analysis and automated identification of mathematics concepts and skills and intelligent tutoring systems. But today he's going to give us a pretty amazing talk, I'm sure, over the tools and resources that you can use to run some of these analysis. So, it's all welcome stuff.
Right. So I'm going to be talking about two things primarily for this seminar series. The first is some of the tools, some of the software approaches that you can use to conducting learning analytics research across the life cycle of an average research process in learning analytics. The second component is going to be, just to make sure that we're all on the same page for that discussion, kind of talking about what goes into learning analytics research, why learning analytics is considered to be a separate field from inferential statistics, kind of the theoretical background for why we need a whole different set of tools to do this kind of work, like why Excel and SPSS is not sufficient for answering questions that you might find in a learning analytics research paper. So what is educational data mining research? We have a paper by Baker and Yosef in 2009 that really hypothesizes that there's 5 different approaches that you can take to doing educational data mining and to doing learning analytics. And throughout this talk, I'm going to use educational data mining and learning analytics fairly interchangeably because they are technically separate fields, but they have a very great deal of overlap, and you can use the two terms interchangeably. So when we're talking about educational data mining research, we're talking about one of 5 or 6 or 7 things, depending on who you talk to. We're talking about using data to predict some kind of outcome. So maybe we have student data for a class that they're taking, and we're trying to develop algorithms that can predict what their score will be on the final exam. We're using clustering approaches. So maybe we have students across an entire school district, and we'd like to cluster these students on different behavioral outcomes like disciplinary referrals. We'd like to cluster them on academic outcomes. And we'd like to try and look for different subpopulations of students that might exist in some broader pool. We can conduct relationship mining, which can be thought of as if-then or if-then-else association rules. Things like, what is the relationship between a student performing behavior X and some outcome Y? Similar to prediction, but looking more in terms of the relationship between these cause and effect variables that we might decide to look at. We can also use educational data mining as an approach for distilling data for human judgment. And this is really where a lot of the learning analytics comes in. EDM tends to be more of an automated approach. Learning analytics tends to take more of a human judgment approach. But you can use educational data mining to distill very complicated, very complex, very rich data sources, the kinds of things you might get from video games, intelligent tutoring systems, and MOOCs, and perform analyses that condense that data down so that it can be used, operated on, and implemented through human actions. And then finally we have discovery with models, or model ensemble, which is where, using some of these other approaches, we can develop a model that describes some phenomenon that might be difficult or otherwise impractical to measure in most classroom settings. An example would be something like student affect, like whether a student's bored, whether a student's confused, whether they're disengaged. We can create a model that describes that student affect by using human coders, and then we can take that model, after we've studied its generalizability and its overall accuracy, and apply it to new sets of data where we don't have human coders and we don't have human developed labels, as a way to make these models more generalizable and more broadly applicable to situations where it might not be feasible to have human coders in every single classroom in the entire Northeast coding student affect. So how is this approach different from A/B testing? Why can't we just use things like an ANOVA or a regression? Well, technically we use regressions in prediction anyway, but regressions are special. EDM and LA are drawing from fundamentally different data sources. If you think about where inferential statistics grew out of, it grew out of this need to have a large unobservable population You could never give a questionnaire to anyone inside, every single person in the United States of America. But you can draw a sample, and more importantly, you can draw a sample and then you can operate on one group, and you can leave the other group out as a control group, and you can use that to draw conclusions. With educational data mining and learning analytics, we have access to scaled technologies that mean we don't even really need to draw samples anymore. For example, if you're working with an intelligent tutoring system, like assessments, and you want to draw inferences about how students use that intelligent tutoring system, you can literally access every student who has interacted with the system. Like, that's it, you have your population. You don't need to draw inferences anymore. And even beyond that, because we're looking at whole populations, we don't need to worry about inference anymore. And in fact, when you're working at data at such scales that we are, data where you have tens of thousands, or even in the largest data sets, hundreds of thousands of students, if you try to perform inferential statistics, it breaks fundamentally. Everything will be significant, even things that are completely and utterly meaningless. Learning analytics and educational data mining represents an approach that focuses on the strength of the different relationships that exist in data, the capacity of these relationships to inform outcomes, and the actionability of these findings on improving some system or pedagogy that you're interested in. And so what grows out of this fundamental difference in the kinds of data and the kinds of analyses that we want to perform is a fundamentally different set of tools to look at the kind of relationships and models that we want to construct. These are extremely diverse fields, far more diverse than most things in inferential statistics. And what results from that is this whole forest of specialized tools that has grown up around the field. Things that individual researchers have developed, things that small teams of researchers have developed to answer very specific questions about what is going on in my particular system of interest. And because of that approach that researchers have taken, and because of that diversity of data that we have access to, there isn't really one field unifying tool like you consider SPSS to be for inferential statistics. And even there, this is kind of something that's starting to seep into inferential statistics as well, and even SPSS is slowly but surely becoming outdated. There's analyses that I've had to run in MATLAB and in R because they're packages, analysis models that simply don't exist in SPSS or aren't appropriately specified in SPSS for the purposes that we need to use them for. So for anyone who's coming into learning analytics fresh and hasn't had a whole lot of experience working with these kinds of data, these kinds of analyses, I want to situate the tools that we're going to talk about and the analytical and methodological approaches that we're going to talk about within the broader cycle of what learning analytics research looks like. So in general, when we have a learning analytics project, we're going to start with some kind of acquisition of data. And data acquisition carries with it its own tools, its own methods that you can use to acquire data from different sources, work data in different formats. From there, generally you have to clean and process the data. It might be very raw action data, it might be data that was never really intended for use in experimental context and very messy and disorganized. We also have to make sure there's not missing values in the data, that there's not improperly recorded values in the data. From there we move on to a step of feature engineering and variable construction, which is where we are constructing meaning out of the data that we have access to. Say, for example, that we have data from an intelligent tutoring system, which consists of student timestamps for different actions that a student takes within the system. An example of a variable that you can construct or a feature that you could engineer is durations in between student actions. That's not necessarily something that the system is going to report because the system isn't set up to report out these different contextual variables like duration. But it can give you timestamps, and you can operate on timestamps mathematically to produce new information from your data. And that's the process of feature engineering and variable construction. From there, once we've cleaned our data, we've developed an appropriate feature set, we've captured a lot of the variance that we believe exists in our data, we can move on to analyses and modeling, and we can start to actually look at the relationships, the outcomes, the strengths of different associations that exist within our data. And this entire process is cyclical, especially the first couple times you do it, and even when you think you're experienced at educational data mining, you're going to find yourself moving between all three of these pretty interchangeably. For example, you might find when you're working on engineering features that you don't know what a certain variable is, and you need to go back and actually check what the data is and reprocess it. You might find that there are missing values that you didn't account for, weird values for data, like maybe some other postdoc working on a project for some reason decided that a problem that doesn't have hint should be coded as -1 instead of 0, defying all logical and rational conventions for using zeros in data, and you didn't realize that until you got all the way to modeling and wondered why your hint coefficient was negative. And now you get to go all the way back to this step and do that again. It's a cyclical process, and each of these steps inform the other one. It's a very iterative process where you're exploring and searching the data for different relationships that could possibly exist. And when you feel like you found something meaningful, then you're going to move on to visualization and publication of those results. You found something interesting, you want to share it, and you want to share it in a way that is easily conveyed to other people through graphical or other visual mediums. And in terms of the amount of time you're going to spend on that process, get used to feeling like you're making absolutely no headway on anything meaningful for about 80 to 90% of your time. Data cleaning and processing and feature engineering, affectionately known as the slog to most people who do learning analytics, is going to take up the vast majority of your time. Because this is the interesting part. We're not doing structured experiments. We're not working with questionnaires that we've developed for a specific purpose. We're taking very raw, very unprocessed data that usually does not have any kind of educational intent associated with it, and we're constructing meaning and we're constructing action from nothing. This is what's going to take most of your time, because if you want to do it well, you need to construct a very rich feature space that encompasses a lot of different sources of variation, different student actions that might be meaningful, from the base logs that you're provided by the systems with which you work. And then you get to analyze a little bit, and then you get to write. So why do we have to do this? Why do we have such an extended process? I touched on some of it. It's because the data is big. We're not working with 30 or 40 questionnaires. We're working with tens, hundreds of thousands of students. We are beyond the scope of doing any of this by hand. This could be contentious, but I don't think there is anywhere in learning analytics research that you would ever hand enter data anywhere ever. Like, just never. You are never going to be hand entering anything when you're doing this. There's so much of it. Documentation and management can be poor, especially for systems that don't really have educational purposes or even diagnostic purposes as one of the goals of the system. You might get data that is only a step or two removed from machine-readable code because the people who are running your system didn't anticipate at the time that they developed it that anyone would ever want to look for traces of learning or traces of behavior or different impactful outcomes in the data that some system provides. And also, unforeseen and lurking problems are frequent, related to the previous two. You know that your data is big, which means you don't always have a good grasp of what exactly is in every single row and every single column. And you also know that documentation and management can be poor, which means you find traps and sinkholes as you wander through the data. You don't really have a good sense of where things are at the outset of the project. So, what are some of the tools that we can use to navigate this minefield of incredibly complex data? Let's start with where you're getting your data from, which technically I didn't build this presentation as being on. We're going to start with, I don't even have data, now what? Some tools that you might want to use, and this is going to look like programming, but don't worry, we're going to touch on it later. Most databases that you're going to be working with are going to be SQL or NoSQL. There's going to be a couple databases that are Hadoop, maybe some special Spark ones, but like 90% of everything you do is going to relate to SQL. If you don't have a data set that you're directly going to, there is a vast wealth of awesome secondary data sets for you out there, where a secondary data set is data that you didn't necessarily collect on your own, but is available for you to obtain and to do research on. And some sources for that would be the National Center for Educational Statistics website, where they have a wealth of interesting longitudinal data, the Pittsburgh Sciences and Learning Center Data Shop, which is a very educationally oriented data repository for researchers across the EDM and LA fields to use. You can use Google Takeout, which I only found out about recently. Google will actually provide you with a service where you can acquire all the information that Google is collecting from you through things like your email, things like the positional coordinates of your phone, and you can pull all of that and you can use it to do analyses on yourself. Like a friend of mine used the positional coordinates from his Android phone to develop the heat map where he spent time when he was spending a semester visiting in New York. And then he plotted it out over an actual geographical map of the city to see where he was going. And then there's also the R dataset subreddit on Reddit, if anyone uses Reddit, which is really just like you get anything from our datasets. It's really cool. If you just subscribe to it and watch it every day or two, you'll generally see an interesting dataset across your radar every couple of days. Like the last one that I saw that I was interested in and downloaded was a register of every boat that is dropped off immigrants at Ellis Island from like 1820 to like 1955. And it was like how many people were on the boat, where it came from, what its name was, what port of call it was registered in. So you do like a really cool visualization of where people are immigrating into the United States over time based on years, and just totally random data will pop up on our datasets, and it's awesome. So do you need to know how to code? I brought up SQL. Does that mean you need to know how to use SQL to do learning analytics and to do educational data mining? And the answer is you don't. Programming is very valuable, but you really don't need to know how to program to do any of these. And I will touch more on that later after we cover the full breadth of things. But if you know that you're going to be working with SQL data in your future, write this down. This is all you need. Select all from table. For anyone who does know SQL, you know exactly what that does. It grabs literally everything and gives it to you. You are erring on the side of caution, and you are taking everything that the database may contain. It may be multiple gigabytes, or, well, probably not terabytes of data, but it's probably going to be multiple gigabytes of data. And you're going to have a lot to sift through later, but this prevents you from having to interface with SQL. It's not a great approach, because you're going to create a ton of extra pre-processing work for yourself later. But if you have someone who comes to you and says, I'd like you to work on this project, I've got this data on a SQL database, and you're like, oh, SQL, can't do it, sorry, I don't know SQL. You can totally do it, just do this, and then put everything in a CSV. So moving on to cleaning and processing data. What are we going to be doing in this step? We're going to be looking for and removing duplicate data. We're going to be dealing with missing data. We're going to be removing or recoding meaningless data, things like zeros or NAs, negative hint counts, test student accounts that might be in your data somewhere. And we're going to be restructuring data. So an important component of the educational data mining process is the idea of restructuring. A lot of times when we get data, it's going to be data in action level. It's going to be every single student key press that every student made in every session that they spent working in an ATS. And that data, well, interesting, is often not the only thing we want access to. We might want to take averages across students. We might want to take averages across problems. The process of restructuring data is taking averages of your data across different levels to produce a resultant file that has one row per student, one row per problem, one row per school, however you want to aggregate the data, instead of the normal industry standard one row per student action. It's a re-aggregation process, and that's an important step of doing cleaning and processing of data, because recontextualizing your file lets you build different kinds of features. So some really good ideas before we get to tools are making scatter plots, heat maps, and box plots. Remember, your data is very big. You can't account for every single lurking problem that could possibly exist. But you can do a good job of making sure that you're catching most of what you can. Scatter plots, heat maps, box plots are all going to help you visualize your data across the entire set. With the heat map, you can see what the general distribution of your data is. Box plots and scatter plots help identify outliers. Scatter plots especially give you an inkling as to what the overall trend in your data is. You can identify potentially problematic outliers. Whether you actually just want to remove outliers completely, or whether you want to consider them as contextual information, is really up to your own discretion. But there certainly can be problematic outliers. Things like, a student who left his intelligent tutoring system online for 2 weeks. And so he has like a duration of 2 weeks somewhere in his data. Obviously that is some kind of error, and you probably want to think about removing it, unless it looks like a persistent behavior that the student is doing or multiple students. You want to count things. You want to know how many students are in this data set, how many problems are in this data set, what's the period of time over which this data was collected, how many rows do I have, how many columns do I have. Calculate some mins, means, averages, deviations. Know the shape of your data, because when your data is as big as the data that you're going to be working with when you're doing this, it's not feasible to go through in a program like Excel and look at every single cell. You need to understand the broader overall distribution and use that as a roadmap to identifying potential problems. That said, Microsoft Excel is a really great tool for cleaning and pre-processing data, on the condition that you can manage to get your data to actually open in it. If anyone has experience working with Microsoft Excel on large data sets, you know that it gives up, like full stop, at over 1 million rows. There is a hard limit on the amount of data that Microsoft Excel can load. And that problem is compounded when you have a high number of columns. Excel really does not handle columns well. So if you have a data set with 100 columns or so, you might only be able to hit 200,000 rows. Anything past that, you're going to run out of system memory, you're going to hit extreme lag. As long as your data set isn't huge, Microsoft Excel is great. It gives you a nice visual interface, it lets you see things that are wrong, you can perform very simple count functions, very simple check functions. It is a really great tool for cleaning and processing data, size appropriate. If you have big data, you have run into the first reason why programming is a very good idea to learn when you're doing learning analytics. Because your approaches to a CSV or an XLS file that you can't open in Excel because it's more than 1 million rows is either split it in half and do everything twice, or move to a non-graphical interface, something like R, something like Java, something like Python. These are programming languages that will help you increase the scale of the data that you can load and operate on at one time, but the trade-off that you make is that you no longer have an easy visual approach. You need to have a much better sense of either checking for errors systematically through, count functions and outliers in every single column, or you need to have a good understanding of where issues might lie and where other issues might just not be important to scale. So after we've cleaned and processed our data, we're going to move on to actually making variables. We're going to be doing some feature engineering. Feature engineering is extremely broad. If you're in the Learning Analytics program, there's an entire class over the course of the semester devoted to doing feature engineering. And that's not even going to cover the extent of features that you can create. But some general ideas of what feature engineering is are things like durations. Very easy to calculate the difference between two different timestamps. You can use duration to infer things like student off-task behavior or concentration. You can fit learning models, such as BKT or PFA. These are models that can infer the structure of student knowledge based on patterns of correct and incorrect responses to your data. And then you can later on use BKT and PFA either as features in subsequent models, or you can use them as labels themselves if you want to study the efficacy of student learning. You can also flag for specific behaviors or action patterns. So let's say that I want to know every time a student uses more than 5 hints in 20 seconds. I could write a feature for that. Maybe I think that they're trying to game the system and just get the system to provide the answer for them without doing any work. That's not something that any system is going to explicitly state, but it is something that I can draw out of the data by, if I'm doing it in Excel, I can write a flag for it, or if I'm doing it in Python, I can write a little true-false flag that flicks true anytime you see the hint, and that counts hints, and so on and so forth. Those are some simple examples of what feature engineering making variables is going to look like. Some tools that you can use for it. These are exactly the same, because data cleaning, data processing, and feature engineering have a lot to do with one another. You're going to be working with the data at a very fine grain size. The difference between feature engineering and data cleaning is in one side of the equation, you're cleaning the data, you're preparing it, you're making sure there's no errors. And on the second side of the equation, you're actually constructing new data. And remember, these processes are cyclical. It's a very good idea to check features that you create to make sure that you haven't created even more missing data, even more outliers, even more weird values. An additional tool that I want to mention here, our first specialty tool I actually think that we've even covered, is a program called the EDM Workbench. The EDM Workbench is just a little piece of Java code that Dennis Rodrigo worked on with a bunch of other authors. And the idea of the EDM Workbench is it looks at the history and usage of feature engineering in educational data mining over the last 5 years, as of 2012. It selects the 26 most commonly used features in a data set, things like off-task behavior, things like hasty guessing, and creates, as long as you tell it what your columns are, an automatic labeling for those 26 features, or as many features as it can identify with the columns that you have access to. So if you have a big data set, and you don't have the programming experience to actually go and make all of your own fancy creative features. The EDM Workbench is a way for you to at least get some mileage out of your data set and do it in a way that has been experimentally validated and used in different models by the rest of the community. And EDM Workbench is free. There's only one tool in this entire presentation that isn't free. One of the great things about collaborating with people who do a lot of HCI and computing research is that they're like super into open source. So let's move on to analysis and model, which in many ways might be even broader than feature. The idea here is that we want to develop models to draw conclusions about our data. We want to generate predictive models. We want to take data from a student and predict what they're going to do, whether they're going to pass, fail an exam, whether they're going to go to college, whether they're going to drop out of high school, different predictions that we can make about students. And we're going to examine clusters and relationships within data. How do these data exist with one another? Are there broad trends? Are there subclusters? What's the overall structure of the data in terms of some outcome variable or pattern of behavior that we're interested in? Thinking back to the 5 motivations for doing EDM research from one of the first slides. We're going to try and do that here. The tools that we're going to use, we're finally getting rid of Excel, are things like RapidMiner, things like Orange. SPSS is also good, and then also, again, you're going to see programming on every single slide. You don't need to know how to program, but damn is it versatile. The idea behind these analyses programs, things like RapidMiner, things like Orange, and this is going to be common with most of the tools that you use in this process. Things like Azure ML, and things like KNIME, and there's like 15, 20 other tools that I'm just not mentioning here. So they're all going to feature something called a workflow. And your workflow looks something like this. Sorry if you can't see it because it's a little bright. The idea is that a workflow is a box where you can put all of the different analyses that you're going to do. You can manipulate those different analyses, you can move around the order and function of things, you can play with different parameters, and you can do it all in this very nice graphical user interface so that you can keep track of overall what are the processes that I'm performing on my data. And this is more important than in something like inferential statistics because EDM and learning analytics are often going to be dealing with things like training sets and test sets, which we don't have to worry about a lot in experimental research because we have control groups. We're going to be dealing with things like cross-validation to make sure that a model developed on one set of data is applicable and equally predictive on other sets of data. These are all complicated processes that we'd really just like to be able to offload to some computing cluster. And that's what a lot of these workflows are going to do. So this is an example of an actual workflow that I'm using in some current research right now with the assessments data that Chad mentioned at the start of the presentation. We're reading in from a CSV. We're selecting our attributes, which is basically removing a bunch of columns that I don't want to include in the data. We're performing a process called forward feature selection, which is where we take roughly the 950 columns that we have in our data, and we empirically select, in terms of overall model fit, we're using 15. We take the 15 best features for the model, the 15 features that put together describe the most variance in terms of our outcome variable. And then we validate that model. We take a bunch of different cross-sections of the training and test set, we apply the same model to these different combinations of training and test data, we average across all of them, and then we look at the average performance statistics, things like the overall predictability of the model, the overall sum of squares, the overall correlation coefficients. There's a way to say, not just for this data, but in general, across multiple different slices of the data, this is the overall strength of the model that we're using. So RapidMiner is one approach you can take to that. The other approach you can take to that is Orange, and Orange is freaking great, which is why I included it here. Like, look at RapidMiner and how horribly complicated and Spartan this Russian nesting doll of folders is. This with like buttons and all kinds of different colors, and like I use RapidMiner, and I'm like, I don't know what half of these things do. But look at Orange. Oh my God, it's awesome. You only have one line, and everything is extremely obvious in terms of what it does. Where do you classifiers? They're right there. There's your regression stuff. It's right there. It's also worth noting, I don't work with Orange a lot because it has the same scale of data limitation that Excel does. It really doesn't handle over a couple 100,000 rows very well. But it does look like, and it's not open, but I was poking around in this in preparation for the study. If you open up data, it actually has a bunch of like pre-processing and error checking and even like feature selection tools. I haven't played around with those a lot, but I think orange might actually belong in some of these slides back here. Like it might actually do a lot of those things. So if you have a data set that you're working on, and it's less than like 400,000 rows or so, and you're like, I don't want to use RapidMiner, like what else can I do? Check out Orange. It's free and it's awesome and everything makes sense, especially when you're like first trying to figure out what research and educational data you use. So we've moved through the cycle a couple times. We pre-processed our data, we did feature engineering, we found mistakes, went back to pre-processing, did analyses, went back to pre-processing. We're finally done. We have a thing that we want to tell the world about. We found some really neat findings. We need to visualize that. Our data is big, our data is complex. Tables do work, but tables are not always the solution when you're working with data that is contextually rich as ours. Visualization is extremely important in this field because it is a way to communicate very complex, very rich data in a way that intuitively makes sense and is graphical and easy to understand. Visualization is a skill. It is something that you have to practice a lot at. It is an art because there are multiple different ways that you can represent the same kinds of data. And there's also a bunch of really expensive tools that you can use to do data visualization. If you have someone backing you, like a grant or a company, get them to buy you Tableau. Because Tableau is awesome and also costs $1,000. But if you want to do good visualization and you lack programming skills, there are not a wealth of options. In terms of visualization, you tend to get what you pay for. And there are some good free solutions out there, things like, creating word clouds are a very good, if not, basic approach to doing visualization. But because of the specialty and the creativeness that comes with producing visualizations, if you lack the programming knowledge to do it yourself, you tend to have to pay for it. So a brief note on text analysis, because if you think back to the slide where we were talking about the 5 fields of EDM research, that was in 2009, which is centuries ago in terms of how fast this field moves. Since that paper was written, text mining has really emerged as this new space for doing learning analytics research, especially in education. Text mining has been around forever, since like the 70s, if you're talking about human-computer interaction and computer systems. It's everywhere. Google was built on text analysis to an extent because they had to figure out how to use search terms. But it's only recently that text analysis has come into doing educational data. The idea here is that rather than analyzing numbers, we're analyzing words. We're analyzing sentences, analyzing documents. We're measuring word co-occurrences, things like terms that are frequently used together. We're modeling latent topics in text, what kind of words tend to give rise to a broader domain structure. We're looking at things like word coherency, tense shifts. We're inferring things about essay quality based on these different features of a student's writing. There's many, many applications for text analysis. And there's many, many tools for text analysis. Some examples here, and again, there's a list of maybe 30 to 40 that I could probably provide you, but these are probably good ideas for someone who's just starting out and just wants to explore these things. There's Tails. The abbreviation for Tails actually escapes me right now. But the idea for Tails is if you're familiar with Cometrics, which is an older program, Tails is an improved version of Cometrics. It looks at 104 different linguistic indices. Things like sentence coherency, things like masculine and feminine neuter use, things like overall sentence length, things like grammatical modifiers, adverbs, pronouns. I am not a formally trained linguist, and this tool is much smarter than I am. The idea is that Tails produces this list of indices based on the text that you feed it, which are then features, and you can go and load them into a model. So some work around Tails has come out of Daniel McNamara's lab at the University of Arizona, looking at things like automatic grading of student essays based on the different kinds of indices that Tails produces when it's fed student essays. Other tools include things like Mallet, which is a topic modeling tool. The Stanford Core NLP, NLP standing for Natural Language Processing, and just a ton else, like Python, R, and Java are on here again, because there's libraries in all of these programming languages that do this. But you can imagine that if the diversity of ways to analyze numbers in educational data mining has resulted in such a proliferation of tools, that when you take something that is inherently complex as particularly the English language, and you try to take approaches towards automated processing of that, you're going to get extreme specialty tools. And there's a lot out there for doing different kinds of things. Finally, a brief note on programming, because we have danced around this issue. Do you need to know how to program to be a data miner or a learning analyst? You do not. But if you don't know how to program, your research probably isn't going to be, not necessarily as good, but it's not going to have as great a depth when compared to someone who can. Your ability, unless you know a really good programmer friend and you buy them lots of lunches, your ability to create features is going to be restricted. Your ability to model and to model in specific ways and setting particular model parameters is going to be limited. Your ability to create visualizations is going to be limited. That's not to say that if you don't know how to program, you can't write a really good conference paper or write a really good thesis or capstone based on educational data mining. What it means is that if this is something that you want to do, and it's something that you want to do well, even after you leave this program and you leave academics, I would strongly encourage you to learn not one but several programming languages. And some of the languages, which might be good, are the ones that have been featured in pretty much every single slide on this presentation. Python is fantastic, especially for doing data exploration and data manipulation. Java is an outstanding tool creation program, very good for developing your own models, your own analyses, and iterating through very large data sets. And R is fantastic for doing most of those things. R started off as a statistical language and has now evolved into almost uninterpreted language, I would say, where there's a great wealth of things that you can do with R. And the reason all of these programs are so flexible is because of things like libraries and because of things like packages. Say that you need to do a logistic regression in Python. There's a library. You can just import it into your Python program and do logistic regression. Say you're doing a topic model, and you know that Dave Bly has a topic models package for R. You can just import that. Well, what if you need a stemmer for your data? Because your data needs to be stemmed and lemmatized. Oh, it turns out there's also a package for that as well. It gives you an amazing flexibility in terms of the scope of research that you can perform when you're able to utilize these programming languages. And again, not to say that you can't do good EDM research. You absolutely can. But you will come to a point, if you don't know how to program, where you want to do something and you are not able to. And to make that even worse, sometimes you come to a point in educational data mining research where you come to a point where you know that there is a programming solution out there, like you might be reading the README for a package that does exactly what you want it to do, and you lack the programming knowledge to implement it. The solution is literally right there, and you cannot grab it. We have time for questions. We have time for applause. Probably. We have an email address if people have questions.
So when it comes to some of the, and I'm new to all of this world,
Great.
just so you know. So when it comes to some of the things that we're actually measuring, for say, like you said, for example, how bored a student is, or how much they guessed, things like that. These, because they're so not measurable, how is all of the stuff that we gather, how do you actually validate it?
So let's use the specific example of boredom, because that's probably the one I know best. If anyone is familiar with Ryan's work, my advisor, Dr. Baker, he developed a set of affect models. And the way we did that was we went into a bunch of classrooms in the Northeast with phones. And on the phones, we had a little program called the Human Affect Recording Tool, or HART. HART was synchronized with Assistance, the tool that students were using. And as the students worked through Assistance, we would have human coders in the room empirically determining whether that student currently looked bored, currently looked confused, currently looked frustrated, and so on and so forth. What we had as a result of that project was we had one set of data over here with timestamps, with the complete record of what a student did in that system. And then over here in another data sheet, we had what affects a student was currently displaying at different times, with timestamps that synced up across both. So what we were able to do is we were able to do feature engineering on the data over here of all the things the students did in the tutoring. We were able to use the affect data over here as a label, the thing that we're trying to predict. And we were able to develop an algorithm that said, okay, take these different features and these different combinations, multiply them by these ways, and that will give you a prediction for whether the student is bored. And then in order to validate it, we went and we conducted a second study where we also took labels, we also took measurements of student affect, we also measured student performances in the system, and we held those labels out. And instead, we took the previously developed model from the previous set of students, we applied those predictions and calculations to the new data, and then we measured their agreement with the empirical observations that we took in the classroom. And granted, that's not perfect prediction. Our accuracies tend to be somewhere between 30 to 60% better than chance, which is not super, but it's also 30 to 60% better than chance if you were just going to flip there and sit there and flip a coin.
Following up on that, that's a fascinating question. How do you trust that the human coders know what boredom looks like?
Extensive training. Doing things like looking at human emotion, because there's been work on the different emotional states that you can display. Doing things like achieving good interreader reliability and accuracy in simulations and control trials. There is a whole certification process around the Baker-Ocampo-Rodrigo monitoring protocol, which is the process of being in the classroom and taking those affective observations, where you have to undergo training in an actual live student setting in order to achieve certification. You have to perform above a certain accuracy in order to actually be allowed to go and do this yourself. So in that sense, we took a very experimental psychology approach to it, where we're saying we need to achieve good interrater reliability. We need to have high accuracy. We're going to develop these big protocols, and everything is going to be very formalized, because those assumptions are the ones upon which the accuracy of all of the affect models that we went ahead and applied rest on. So that is the part, more than anything else, that needs to be done to lab standard. Other questions? Those are good questions.
Stefan,
Yes.
does Orange have student level cross-validation?
Yes, it does. The thing about Orange is that it doesn't have, if you look at the folders over here, which you definitely can't see, but so here for modeling in RapidMiner, I have 249 different models and analyses that I can. That is not a number that you're going to get anywhere close to much. It's going to give you like 5 or 6 different approaches for regression and classification. But it's still going to let you do things like forward feature selection, cross-validation, batch cross-validation, and student cross-validation. It's going to give you all the tools that you need to do a basic analysis. It's not going to get quite as rich as things like RapidMiner or Weka or 9, but it's also, in my opinion at least, well suited to smaller projects like first projects, rough drafts, pilots, things like that. If anyone does use this and figures out if it can actually do like good feature engineering, let me know, because that would really convince me to use it a lot more. Yeah,
Does Google Sheets have the same limitation as Excel?
roughly.
Roughly, like is it larger?
You're not going to be able to get more than 1 million rows into Excel or Sheets. And Sheets, in my experience using Sheets, is actually even slower than Excel is for similarly sized data. Both of them have an upper limit on the amount of data that you can load. And to be fair, so too do R and Python and Java, but they're upper limits that you're not going to see unless you're working for like Amazon. They're not upper limits that you're going to see collecting educational data on anything less than a national scale. Yeah.
I have another question. Can you elaborate a little bit more on why inferential statistics breaks down and why you can't focus on effect sizes and do cluster analysis and control for enough variables that you were looking at subgroups? Can you just explain a bit better?
You certainly can. You certainly can, and most people have shifted to looking at things like effect sizes. The broader idea is that inferential statistics is structured in such a way that it allows you to pull conclusions out of a sample of data. It assumes that you're working with some group of individuals that is necessarily smaller than the population you're drawing them from. And so the structure of the way in which you go about proving a claim in inferential statistics is fundamentally based around that assumption. And it's assumption that, depending on what data sets you're looking at, can be violated when you're looking at research at the scale that educational data mining and learning analytics is. It's not necessarily that, I mean, it's definitely, there's issues with p-values, right? There's lots of issues with p-values in terms of things like the false discovery rate, in terms of things like, running multiple tests. There's issues with p-value. And effect size and clustering and so forth is better, but it's better in the sense that it is a proviso for a form of measurement and conclusion inference that's still based on this assumption. And so I guess what I would say is if you have a data set that consists of 15 to 20,000 students, what is the argument for using inferential statistics over data mining when data mining is explicitly structured to explore the kinds of questions that you might have about a data set that big? Clustering, yeah, we do clustering. We're good. And like we brought up regression too, but there's slightly different forms of regression where we're focusing less on the significance criterion and testing a null versus alternative hypothesis, and more coming in with the assumption that experimentally we could validate any relationship that we wanted to, and instead we should focus on just a priori trying to find the things with the highest effect sizes. Like we've got all the data, let's look at the places that are going to have the highest impact, because we're able to do that by virtue of the size of the data that we have. Other questions? Am I good on time? You didn't give me any of the cards. So
You got enough time for about one more.
Sweet. Pretty good for only like practicing this once in my head. No questions? It's fine too. Yeah.
What are your top pieces of software that you use?
I use Python for lots of stuff. So I use Python for data cleaning and processing because it gives me the ability to keep a record of the different things that I've looked at, which is something that I actually didn't touch on at all. When you're doing this, you really want to, when you're doing this, you want to keep a record of what you're doing. You want to be able to go back and look at the steps that you took. And doing that in a programming language is a very easy way to approach version control, because I can go back into the script that I wrote and I can look at exactly what the operations were that I performed. If I wanted to do that in Excel, I'd need to save a new sheet or maintain an extra README outside the file to tell me the specific formulas that I used and the specific sortings that I did and the specific filterings that I used to calculate different variables. Whereas when you take a programming approach to that, and this is true in R as well, if anyone wants to use R, you have the record right there in your code, in your workflow. And so I find that a really attractive option for doing cleaning and processing data, as well as feature engineering, because it gives you a record of what you've done. It's very easy for documentation and replication. When we get to analysis, I use RapidMiner mostly because I don't know how to use KNIME yet. RapidMiner has some issues that I have run into lately, specifically around trial versions versus full versions of RapidMiner, not giving me access to all the RAM that I need to work with the size of data that I have. So I'm trying to teach myself KNIME, which I didn't cover because it looks almost exactly the same as RapidMiner, just slightly different. And then also, I will use programming languages here, like Python and R, but usually only by necessity. Like if I can't find an algorithm in RapidMiner, or if I can't find an algorithm in KNIME, then yeah, I'll find somewhere in scikit-learn in Python or somebody built that out. But I mean, I like programming because it gives me a record, but I mean, so does RapidMiner. Using programming languages can sometimes kind of suck. I'm not a masochist. And then for Viz, I mean, I don't make interesting visualizations. I just use tables. I'm not good at it. It's an art, and I'm not good at that particular art. We all have things we have to work on.
Word class.
Yeah, I've played around with a couple visualizations in like Python, but also, I mean, you could just use Excel. Like Excel makes charts, SPSS uses charts, and when you put them in your presentations and paper, everyone's going to know that they're SPSS and Excel charts, because they all look the same, but I mean, if you can make them work, you can make them work. As long as they convey the information in a meaningful way. And that's what the goal of visualization is.
Have you considered kind of reaching out either for free or for small amounts of money to have someone do visualizations for you in your pursuit like research?
If I came to a point where I felt like I needed to, I think I would. My experience has been that I don't need to produce high quality visualizations for conference papers. And I have not yet given a conference talk that has been important enough to warrant really nice visualizations. Like, I'll still use Excel pie charts and stuff. Now, if I was giving like a, keynote or something, yeah, I'd probably want that. But yeah, I've never felt pressured to go to someone externally for doing data viz. And maybe for an industry that changes, because presentation is a little more important there. But yeah, it's certainly an option that you could take if you felt like you really needed a high quality visualization or something. Or you had an idea of what you wanted to do, but you just couldn't implement it. Like you had this idea in your mind and you just couldn't manipulate the data yourself.
All right, I think that about does it. All right, thanks, Stefan.
Thank you guys.